In this lesson, we're going to talk about lenses. There are two main types of lenses, a converging lens, a convex lens, and a diverging lens or concave lens. And converging lenses, convex, have the same shape on the outside as a convex mirror, and concave lenses have the same shape on the outside as a concave mirror. You can remember the converging and diverging terms because in a converging lens or convex lens, these are the ones that are thicker in the center and thinner in the edges. If the light comes through them, it converges to a single point. And in a diverging lens, which are thinner in the center, if parallel light comes through it, it diverges after it exits. Let's look at the parts of a convex lens. A convex lens has, just like mirrors, some of these parts will be similar. We have optical axis straight through the center. We also have a focal point. Now there's two focal points on a lens, but the main focal point for a convex lens is on the opposite side. This is where if parallel light came through, it would all converge to that focal point. We also have a near focal point. This is on the side of the object of the lens. And if we had light that traveled through this near focal point and then hit the lens, it would travel at parallel rays after it went through the lens. So it's the same distance, focal length f, from the lens. It's just on the opposite side. So this is the near focal point, and the same distance away we would have the far focal point. The focal length is the distance from the lens to the focal point. So we're only going to be considering thin lenses. This simplifies the refraction of the light inside them to some basic equations that we can use. So let's look at the rules for a converging lens. If we have parallel rays coming into the lens, for a converging lens, all those parallel rays will be directed to the far focal point. We also have a converging lens. If we have light that comes through a near focal point, that light will be refracted to come out at parallel rays on the other side. And finally, any light for a converging lens that goes through the center of the lens will continue in a straight line on the opposite side. So any way that it comes in, if it crosses through the center, it doesn't refract at all. So let's consider a couple of cases for the converging lens or the convex lens. First, let's say our object is farther away from the lens than the focal point. The focal point's here and our object is further away. We're going to consider three special rays following the three rules for convex lenses. So first, we have light coming from the top of the object parallel to the principal axis, and it will be directed through the far focal point. We also have light that travels from the top of the object through the near focal point, and that, when it hits the lens, will travel at a parallel line to the principal or optical axis. And finally, we have light that travels straight through the center of the lens, and that will just continue in a straight line. These three lines all converge at one point. We labeled it P here. This is where the top of our image will appear. So all rays will converge on the opposite side. The result is a real image because the light actually travels to the image. In this case, it is a flipped image. It's upside down. And depending on how far the object is from the focus, we could have an image that is smaller, equal size, or larger. So you'd have to do a ray diagram. There's no general rule for this particular case. What we do know is it's always real and it's always flipped. The magnification will change depending on how far away the object is. All right, let's consider another case. Let's say we put our object between the focal point and the lens. What is the image going to look like? So when we draw our three rays following the rules, we have a parallel ray, a ray that comes from the focal point, and a ray that goes through the center. These rays all diverge on the other side of the lens. They don't converge. So we're going to treat this similar to convex mirrors. We're going to, instead of trying to look for an image on this side, since there is no converging on this side, we're going to go backwards, and we're going to say, let's say these rays, let's find the source they came from, going backwards until they converge, and we will find a location for a virtual image. And so in this case, our image will be on the same side as the object. No light passes through it because the light goes this direction. So this is going to be a virtual image. Now you'll notice we have a larger image than the object itself. This is the exact setup that we would have when we use a magnifying glass. So for a magnifying glass, you know that you have to hold it close to the object. You hold it close so that the object is closer than the focal point of the magnifying glass. And what that does is it creates a virtual image that you can see that's larger than the object itself. All right, the third case for a converging lens or convex lens is when the object is at the focal point. So our three special rays, our first is parallel and it goes through the focal point. Our second goes through the center and keeps traveling. The third would actually go through the focal point, so that's not going to even go through the lens. The result is these rays do not converge, but even if I extended them backwards, they're parallel, so they'll never converge. So if I have an object exactly at the focal point for a convex lens, I will have no image. All right, now we're going to look at the second type of lens. This is a diverging lens. In a diverging lens, all of the light on the opposite side diverges. It does not converge to an image. So what are our rules? First, parallel rays coming in they diverge, so that means that they diverge along a line that will begin at the near focal point. So we can find the direction of this ray by tracing it backwards to the near focal point. And any ray that comes in parallel diverges as though it were coming from the near focal point. We also have light that comes in headed towards the far focal point, and that light that comes in headed towards the far focal point will emerge parallel to the optical axis, so it comes out parallel. And finally, just like on a convex lens, any light that travels through the center will just continue in its original direction. The ray is not going to be bent if it travels through the center. It goes in a straight line. So for a diverging lens, our rays are always going to diverge. They never converge to an image on the other side. So the image is going to be drawn by extending these refracted rays backwards to find where the virtual image will appear. So all images for diverging lenses are going to be virtual because the light itself travels and diverges. It doesn't converge to an image. So they're all going to be virtual, they're all going to be upright, and they're all going to be reduced in size. All right, let's look at our sign conventions for lenses. So if I have either a convex lens or a concave lens, what kind of signs am I going to use for the image and the focal points? First, the focal length is going to be positive if the lens is convex. So for this lens, my focal length, this is going to be, for lenses, this side you'll see is the positive side. And the focal point that I use for convex lenses is on this side. So our focal length will be positive. For a concave lens, the focal point that I use is going to be this focal point. So that our focal point will be negative for a concave lens. The image for a convex lens is going to be positive. Well, actually, if the image is real, it's going to be to the right of the lens. We're going to have a positive image length. So this is the positive side. So if our image appears over here, which will be in some cases, for the convex lens, then we'll have a positive SI. SI will be negative if the image is virtual and to the left of the lens. This is the negative side. So sometimes for the convex lens and always for the concave lens, we'll have an image that's negative. the distance of the object is always going to be positive. So in mirrors, I just want to point out that in mirrors, the positive side was going to be on the object side of the mirror because we were getting images to the left, or because we were treating the side of the object as being positive. In a lens, the positive is on the opposite side because the light travels through the lens. So this is going to be positive for the lenses, and the side with the object is going to be negative. All right, so let's do a problem. Let's say we have a 4 centimeter tall light bulb at distance 45 centimeters from a convex lens having a focal length of 15.2 centimeters. What is the image distance and the image size? So here are our givens. We're going to use our mirror equation or lens equation for this. We plug in our values. Now, in this case, we have we're using a convex lens. So since it's a convex lens, our focal point will be a positive number. And after we do our calculations, we find that our image is going to be positive also. That means that our image will be behind the lens, or over here to the right. Now we can find its magnification by plugging in our values, and we get 1.99 centimeters for the height of the object. So that tells us that the image is going to be on this side, which means light passes through it, so it's real. We know that for a convex lens where the object is further than the focal point, so that's going to be, this is our focal point, 15 centimeters, and our object is further away, we know that it's going to be inverted. It's going to be real, and from our calculations we also see that it is smaller than our original object.